All right, so in this problem, we actually did this in class, but I know some students probably wanted to look it over again. So in this scenario, we're just solving for flux. We're not solving for electric field. And we have two equations for flux, which in the equation sheet, it shows E dot dA. But we also know that flux is equal to Gauss's law, which is the enclosed integral of E dA, which is Q enclosed over epsilon naught. Now I had students ask, what's the difference between this top expression and the enclosed integral expression? Usually this top expression is when you want to find the flux through a flat surface, like just a plane, and we use rainwater falling through a flat surface for that example, or falling through like a square hoop. And then this is the expression you would use when you have Gauss's law and you're trying to find flux through an enclosed surface like a sphere or a cylinder. So we are going to use the second one. And the most obvious expression to use, we're given sigma, and we do have an expression to get Q enclosed from sigma, which is the fact that sigma is equal to Q enclosed over area. And we do have the area because if I'm just trying to find the enclosed charge, the charge is enclosed in this area right here, which is the circumference of a circle. Now, when we solve this, I'm going to show you both methods, one with Q enclosed and one with E dot dA, and you can see that they actually pan out to be the same expression. The reason why it's harder to use E dot dA is because you would have to know what the electric field is of a plate of charge, and most students don't know that off the top of their head, but we will derive it and then we will show that it does come out to the same solution. It was derived in video 2 of 8.6, and so in class today, students just remembered that, or they looked at their notes and they just plugged that equation in. Okay, so let's start with this expression first. Flux is equal to Q enclosed over epsilon naught. Well, I know Q enclosed is equal to sigma A, or sigma times the circumference of that circle. I'm going to leave it A for now because I know that I can plug in all the values later. Now we're going to solve using the left side of Gauss's equation, which is sigma is equal to the enclosed integral of E dot dA. What this requires is that I actually solve for the electric field, and so I'm going to use Gauss's law. And solve for that electric field. Again, students memorized this or got it from video 2, but let's solve it together. The electric field is going to go through, let me use a different color, the top end cap and the bottom end caps of my cylinder, which means the area is going to be the circumference of the top and the circumference of the bottom. I'm going to call this 2A because I represented the circumference as A in my expression on the right. I am going to also solve for Q enclosed, which I already did. So I'm going to plug that in, sigma A over epsilon naught, and then I can reduce this and see that the electric field is sigma over 2 epsilon naught. Now when I plug that back up into my expression, I get sigma over 2 epsilon naught times dA. And I already said dA was 2A. And so when I simplify this, I also get sigma A over epsilon naught. This should match this, and it does because both of those expressions give me flux. Now, again, you're doing 2 bits of work when you solve it on the left side. But if you memorize the electric field of a plane of charge, then that would reduce the amount of work you have to do. They actually want a numerical value. So I'm going to plug in the numerical value for our flux equation. 12 times 10 to the negative 6 is my charge density. And then my area is pi times r squared, so 0.25 squared, over epsilon naught, which is in your equation sheet, 8.85 times 10 to the negative 12. When you plug that in your calculator, you get 2.66 times 10 to the 5th, and this would be newtons per coulomb meters squared. Now, you might think that is your final answer, but if we look at our diagram, that's the flux going out the top and out the bottom, because we took the area of the top and the bottom of our cylinder as our Gaussian surface. So if we just want the flux through the top, we need to take half of the flux that we got in our problem, and that really is 1.33 times 10 to the 5th newtons per coulomb meters squared. So this is all part A, but everything else should be pretty easy. The flux through the bottom, it's pretty obvious that the flux going up is the flux going down, so you can literally just copy what you got from part A. The flux through the sides of the cylinder, if you look at the sides of the cylinder here in purple, all the electric field lines, even if I were to go outside of my cylinder, they're going straight up and straight down. So if you think about anything entering or exiting the sides of the cylinder, it's 0. So for C, the answer you would get here is 0. And then for part D, it says, what is the net flux through the cylinder surface? Well, we already solved for the net flux. It is the sum of the top and bottom coming out of my end caps. And remember, flux going out is positive, so it's going out at the top as 1.33 times 10 to the 5th, and it's going out at the bottom as 1.33, so you do just add them together as 2.66 times 10 to the 5th. I'm not going to write the units in because that's more time and you know what they are. But the last bit, does the length of the cylinder affect the magnitude of the flux? The flux is the number of electric field lines. If I draw a cylinder that goes all the way up here and all the way down here, does it change the amount of electric field lines if I could extend them up? I see 2 electric field lines going up and going down, and no matter how long I make that cylinder, it will always be 2 electric field lines going up and going down. Flux doesn't change based on height, and so for problem part E, the answer is no.